Do you actually know what it means to try to cross a galaxy? Not just visit a nearby star, but go from one side of the Milky Way to the other. The Milky Way is about 100,000 light-years across. 1 light-year is the distance light travels in a year, moving at about 186,000 miles per second or 300,000 kilometers per second. Multiply that out, and 100,000 light-years is roughly 590 quintillion miles, a 59 followed by 19 zeros. In kilometers, it is around 950 quintillion. At that scale, normal travel times stop making sense. Even if you could move at the speed of light itself, which no ship with mass can do, you would still need about 100,000 years to go from one edge of the galaxy to the other. That is the starting point, the easy mode number, and it is already far beyond any human time frame. Now ask this: how does 100,000 years compare to the timelines of real civilizations? Human recorded history from the first cities to now is maybe 5,000 to 6,000 years. Our entire industrial, high-tech era, the part with electricity, computers, rockets, is around 200 years. So even if you had a magic starship that could move at light speed, a full galaxy crossing would take on the order of 20 times all of human written history, and about 500 times the length of modern technological civilization. That is at a speed you cannot actually reach, with a ship you cannot actually build, in a universe that does not allow massive objects to hit that limit anyway. So before you talk advanced engines, alien megastructures, or future tech, you have to deal with this. The raw distance of the Milky Way already stretches far beyond the lifetime of normal species and cultures. And you're not even at the centre of this system. You're not in some prime location that makes travel easier. Our Sun sits about 26,000 light-years from the galactic center, in one of the spiral arms, not too close to the dangerous core, not too far out in the thin edge. In miles, that is roughly 153 trillion miles, or about 246 trillion kilometers, from the center of the galaxy. The Sun, and everything orbiting it, including Earth and you, is moving around that center at roughly 500,000 miles per hour, about 220 kilometers per second. One full orbit takes about 250 million years. That single year on the scale of the galaxy is 250 million Earth years. Now line that up against biology. Anatomically modern humans have been around for maybe 300,000 years. That is just over 1,000th of a single orbit of the Sun around the galaxy. Your entire species, from the first Homo sapiens to smartphones and rockets, fits inside a barely noticeable slice of one galactic year. If you zoom out to that scale, human civilization is not even a long event, it is a short flash. So here is the uncomfortable question. If you are tiny compared to one orbit around the galaxy, what does it really mean to plan a trip across its full width? To make this more concrete, look at what we have actually built. Voyager 1 is the fastest and farthest human-made object so far. It was launched in 1977, used gravity assists from the giant planets, and is now moving through interstellar space at about 38,000 miles per hour, 17 kilometers per second. For getting out of the solar system, that is impressive, but compared to galactic scales, it is extremely slow. At that speed, it would take more than 17,000 years to travel just 1 light-year. The nearest star system, Proxima Centauri, is about 4.2 light-years away. For a Voyager speed craft, that is over 70,000 years each way. Now stretch that calculation to the full diameter of the Milky Way. At Voyager 1's speed, crossing 100,000 light-years would take on the order of 7 billion years. For comparison, the Sun is at about 4.6 billion years old, and it has maybe 5 billion years left before it turns into a red giant and destroys Earth's habitability. A Voyager-style crossing of the galaxy needs longer than the current age of the Sun, and similar to its entire life expectancy. By the time a probe like that reached the other side, the entire solar system would be radically changed or gone. So you might push back and say, "Oh, GeoVoyager is slow, we will build faster ships, we will use better engines." That sounds reasonable, until you look at what our most powerful rockets actually do. and what the hard limits of chemical propulsion look like. Take the Saturn V rocket, the one that took Apollo missions to the Moon. Its upper stage, the S4B, had a specific impulse of about 421 seconds. In simple terms, that means its exhaust was leaving the engine at about 4.1 kilometers per second, roughly 9,200 miles per hour. For climbing out of Earth's gravity and heading to the Moon, this was more than enough. But when your target is another star, or the width of the galaxy, numbers like 9,000 miles per hour are effectively zero. Light moves at about 670 million miles per hour, about 1.08 billion kilometers per hour. Saturn V's exhaust speed is a tiny fraction of that, and the rocket itself never gets close to its exhaust speed anyway. The basic problem is this: with chemical rockets, you are limited by the energy stored in chemical bonds. There is only so much push per pound of fuel. To reach even a small fraction of light speed, you would need a ridiculous mass ratio, meaning your rocket would have to be mostly fuel, stacked in stage after stage. As you add more fuel, the ship gets heavier, and you need more fuel to accelerate that extra fuel. It becomes an exponential curve. At some point, the rocket is so huge and impractical that it might as well be impossible. You cannot just keep scaling up a Saturn V until it becomes a galaxy cruiser. The physics cuts you off. So where does that leave you? You have a galaxy that is 100,000 light years across. You have orbits that take hundreds of millions of years. You have real spacecraft that take thousands of years just to go a single light year. And you have propulsion tech that is already close to the limit of what chemistry can do, yet still gives you speeds that are basically standing still on galactic scales. This is why many scientists talk about effective impossibility. There is no single law written in the sky that says no species may cross a galaxy. In theory, you can imagine advanced fusion drives, antimatter, propulsion, huge laser systems pushing sails at a good fraction of light speed. You can imagine a civilization far beyond ours, with industry spread across many planets, building engines we can only outline on paper today. But even if you allow all of that, you are still facing distances and times that run into hundreds of thousands to millions of years. You are still fighting the fact that stars move, the galaxy evolves, and civilizations have to stay stable across absurd spans of time. So the first barrier is not exotic physics. It is simple scale. The Milky Way is so large, and your place in it is so short-lived, that crossing the whole thing stops looking like a trip and starts looking like a project that has to survive longer than species usually do. But even if you accept that, even if you say, fine, we will build extreme engines and aim for extreme speeds, you hit the next harsher limit. The universe itself has a speed ceiling that no ship with mass can break, and the closer you get to it, the more the energy cost explodes. You can't just go faster. The universe literally rewrites how energy and time behave to stop you. Start with the basic wall, the speed of light. Light in a vacuum moves at about 186,000 miles per second, 300,000 kilometers per second. That is not just a big speed. It is the hard ceiling built into the rules of space and time themselves. According to special relativity, anything that has mass, even a tiny amount, can never be pushed all the way up to that speed. You can get closer and closer, but the closer you get, the more brutal the price becomes. At low speeds, like cars, planes, even regular rockets, if you want to go faster, you just add more fuel, more engine, and the energy you need goes up in a fairly simple way. But as you start getting near a serious fraction of light speed, that relationship breaks. Your kinetic energy, the energy of motion, doesn't just scale in a neat linear way anymore. Each extra mile per second you add to your speed costs more energy than the last one, then much more, then absurdly more. The universe starts charging you a kind of penalty for trying to outrun its speed limit. So ask this: what happens when you stop talking in theory and plug in a real starship, with a real mass? Take a starship that weighs 1,000 tons, about 2.2 million pounds, which is in the range of a big ocean ship or a very stripped down interstellar craft with people, life support, structure and engines. Now say you want to push that thing to just 10% of light speed, about 18,600 miles per second, 30,000 kilometers per second. That is still way below the actual light speed limit, but already deep into relativistic territory. To reach that speed, you're looking at kinetic energy on the order of 4.5 sextillion joules, written as a 4.5 with 21 zeros after it. In human terms, that is roughly comparable to the total energy used by our entire civilization over tens of thousands of years. All the electricity, all the fuel, all the heat, all the industrial use, everything humans consume over huge chunks of history, dumped into a single burn just to push one relatively modest starship to 1/10 of light speed. So then you might say, fine, but once you're that fast, can't you just coast? Doesn't that at least make the trip manageable for the crew? And that is where time dilation walks in and also tricks you. Relativity does give you one strange gift. As you move close to light speed, time for you on the ship runs slower than time for people who stay behind. At 90% of light speed, 0.9 c, clocks on board tick noticeably slower than clocks back home. From the crew's point of view, long journeys can feel shorter. You could, in principle, cross big stretches of the galaxy in what feels like a few million years of ship time, maybe less with even higher speeds. To the travellers, it might look like they hacked the distance problem. But here is the catch. The galaxy itself does not care about your local clock. From the outside, from the point of view of the Milky Way, and from the point of view of any species that launched you, the trip still takes what the distance demands, hundreds of thousands to millions of years of galaxy time. Civilizations back home still have to survive for those full, brutal durations if they ever want to see a message or a descendant of that mission. Time dilation helps the crew feel less of the pain, but it does nothing to fix the basic mismatch between travel time and how long societies stay stable and alive. And the problem gets worse as soon as you ask the next question. What if you want to go faster than 10% of light speed? What if you aim for 20%, 30%, half, or even 90%? If you doubled your speed from 10% to 20% of light speed, you might think, okay, that probably needs twice the energy. But with relativity in play, that is wrong. The kinetic energy grows faster than the square of the speed, and the relativistic correction makes it even worse. The jump from 0.1 c to 0.2 c costs you several times more energy, not just double. By the time you reach half of light speed, 0.5 c, the energy in that 1,000-ton ship is so huge that it starts to become comparable to what stars output over long periods of time. Push closer to 0.9 c, 90% of light speed, and now you're talking about energy budgets that look like a serious fraction of a star's entire lifetime production of usable energy. For one ship, not a fleet, not a whole civilization, just a single payload. The universe is basically telling you, you can have speed, but the bill is measured in star-level power. So then another issue hits. Getting up to that speed is only half of the story. You do not just want to launch a bullet through the galaxy and smash into whatever is on the other end. If you ever want to slow down and actually arrive alive, with a speed you and your hardware can survive, you need to brake. And to brake from a high fraction of light speed, you need to get rid of almost exactly the same amount of energy you spent speeding up in reverse. That means every scary energy number you have heard so far, every this is tens of thousands of years of human power use, every this is a big chunk of a star's output, you have to double it if you want a round trip or even just a controlled arrival. Accelerate up, then decelerate down. Each leg costs you. Otherwise, you are not crossing the galaxy, you are firing a relativistic weapon into it. So stack it all together. There is a hard speed limit you can never reach, energy costs that explode as you come close, time dilation that only helps the travellers while leaving the rest of the universe waiting for ages, and a mandatory braking phase that doubles the entire energy bill. That leads straight into the next problem. If the speeds you need demand energy on the scale of stars, who or what is actually paying that bill? And how do you even begin to build the machines that can deliver that much power for that long? That is where the story turns from really fast ships into you need the energy budget from hell. To cross the galaxy, you don't need a rocket. You need the kind of energy we normally associate with stars. So the question is, Has anyone even tried to design something that steps into that territory? Not a sci-fi ship, but a serious worked-out concept. One of the wildest real studies we've ever done is called Project Daedalus. In the 1970s, a group of engineers and scientists in the British Interplanetary Society sat down and asked, with near-future physics and optimistic engineering, how fast could we get to a nearby star? Their answer was not a cute little probe on a chemical rocket. It was a 2-stage nuclear fusion-powered starship designed to run uncrewed for about 50 years and reach a target star roughly 6 light-years away. Dedalus was huge. The design called for around 50,000 tons of fusion fuel, a mix of deuterium and helium-3. The exhaust from its fusion engines was expected to shoot out the back at around 6,600 miles per second, 10,600 kilometers per second, which is over 3% of light speed. That is insanely high performance compared to chemical rockets. With that, Dedalus could, on paper, reach about 12% of light speed, 0.12 c. That would get it across a few light years in a human lifetime, and that sounds impressive until you check the scale. That is still only single-digit light years, in a galaxy that is about 100,000 light years wide. So ask the obvious question: if it takes 50,000 tons of fusion fuel and a starship the size of a small asteroid to do a flyby of a star 6 light years away, what does it mean to scale that up to galaxy level? You're not multiplying by 2 or 10, you're multiplying by about 16,000 to go from 6 light years to 100,000. The numbers explode. You end up in a regime where you're not talking about a ship or a fleet, but about industrial efforts that chew through entire planets worth of material and energy just to push a few vehicles to a fraction of light speed. Now look at a very different idea, one that is actually being studied right now, Breakthrough Starshot. This project does not even try to move a big ship. The plan is to use a giant ground-based laser array on the order of 100 gigawatts to push tiny gram-scale spacecraft attached to ultra-thin light sails. The goal is to hit speeds of 15 to 20% of light speed and get to Alpha Centauri, about 4.4 light-years away in 20 to 30 years. Each one of these little sails might need about 1 trillion joules of energy from the lasers, roughly the output of a large power plant running flat out for several minutes, to accelerate something that weighs about as much as a paperclip. That is what it takes to give a gram a serious fraction of light speed. Not a ton, not a car, not a building, a gram. And remember, that is just for the boost phase, just to get it going. So the next question basically punches you in the face. What happens when you stop playing with dust and start talking about moving something the size of a real starship? Say you want a city-sized dark ship, something that can actually carry a large population, full life support, radiation shielding, engines, and all the gear needed to survive in deep space for a long time. A ballpark number for that could be 1 billion tons of mass, around 2 trillion pounds, or about 10 to the 12th kilograms. Now compare that to the gram-scale sails in Starshot. 1 billion tons is 1 trillion times heavier than a gram. If a single gram needs around 1 trillion joules of laser energy for a short 4 light-year hop, scaling that up even crudely tells you that a billion-ton ship at similar speeds needs energy on the level of what a star outputs, sustained for long periods. You are now in the territory where your propulsion system is not just a big engine, it is a civilization-scale power project. You're trying to feed star-level energy into a ship, not once, but over and over if you want more than one mission or more than one direction. That is why people say that crossing the galaxy with big physical ships starts to look like a stellar engineering problem, not a transport problem. And this loops back to something Daedalus quietly assumed in the background, the infrastructure. Daedalus did not just say, use fusion fuel, it specifically leaned on helium-3, a rare isotope that is not easy to get on Earth. The designers suggested mining helium-3 from the atmosphere of Jupiter, using gigantic floating refineries operating for about 20 years to gather the tens of thousands of tons needed. That implies a solar system that is fully industrialized, with automated mining systems, processing plants, orbital assembly yards, and the ability to move huge masses around with ease. And what was all of that for? One uncrewed mission, one way, to one nearby star system, with no braking at the end, just a high-speed flyby. Not a cruise across the galaxy. Not a network of ships. One shot to a star a few light years away. If that is the level of effort for a single local mission, you can see how quickly let's cross the whole Milky Way goes from ambitious to basically absurd. So the pattern is clear. When you move from chemical rockets to fusion and giant lasers, you do get better performance, but the price tag in energy and infrastructure jumps from national level to a planetary level, and then to multi-planet or system-wide level. That is where the Kardashev scale comes in, a way to roughly classify civilizations by how much energy they can access. A Type 1 civilization can use most of the energy available on its home planet. A Type 2 civilization can harness most of the power output of its star, maybe using structures like Dyson swarms, huge clouds of collectors wrapped around the star. A Type 3 would be using much of the energy output of an entire galaxy. When you look at the numbers for relativistic travel of big ships, crossing not just a few light years but a significant chunk of the galaxy, it does not look like a Type 1 or Type 2 hobby project. It looks like a Type 2 plus problem at minimum, something where you are diverting a serious fraction of a star's total power output, possibly for years, to accelerate and decelerate huge vessels. And that is just the travel part, not counting life support, shielding, repairs and everything else. Now connect that to what we actually see when we look out into space. With modern telescopes we can detect waste heat, infrared signatures, and large structures around distant stars if they're extreme enough. We see lots of normal stars, galaxies, gas clouds, black holes, and so on. But we do not see obvious, unambiguous evidence of Type 2 or Type 3 civilizations, no clear Dyson spheres, no galaxy where the light is heavily reprocessed by massive engineered shells. That silence does not prove that no one is out there, but it does suggest that if galaxy-crossing travel requires star-level energy, almost nobody is paying that bill in a way we can see. So you end up with a harsh conclusion: the raw energy required to push macroscopic ships to meaningful fractions of light speed and then slow them down again over galaxy-sized distances looks like the domain of civilizations that can handle power on the scale of stars. We do not see those, and we are nowhere near that level. And even if someone could reach the SAT energy tier, another problem kicks in because space is not empty, and when you move that fast, the thin gas and dust between the stars turns from harmless background into a continuous high-speed sand blaster that can rip your ship apart over long distances. At interstellar speeds, a grain of dust hits you like a bomb. Space looks empty, but at the speeds we've been talking about, it really isn't. Between the stars, you're flying through what's called the interstellar medium. On average, that medium has around 0.01 to 1 particle in every cubic centimetre. So in a space the size of a sugar cube, you might have a few atoms of hydrogen. In some regions, the density jumps way up. Molecular clouds can reach from hundreds to 1 million particles per cubic centimetre. By Earth standards, that is still a very good vacuum, much better than what most lab pumps can achieve, but it is not nothing. If you're crossing light year after light year at a big fraction of light speed, those few particles add up. Now add dust, not just single atoms, but tiny solid grains like microscopic bits of rock, carbon or ice. You might think, it's a microgram of dust, that's basically nothing. At normal speeds, sure, that is harmless. At 0.1 c, 10% of light speed, that same microgram hitting your hull head-on carries the kinetic energy of a hand grenade. It can punch through armour, vaporize material, and spray high-speed fragments inside your ship. Pushed to half the speed of light, or 90%, and per gram of dust, the energy gets into small nuclear weapon territory. You're effectively flying into a constant hail of high-energy bullets, except the bullets are almost invisible until they hit. Breakthrough Starshot, the gram-scale sail project, already has to take this seriously at just 0.2 c, 20% of light speed, and over only a few light years. Their estimates say that each square centimetre of sail will be hit by around 1,000 dust particles larger than about 0.1 microns during a trip of just a few light years. That is over an area the size of a fingernail, and over a distance that is tiny compared to the size of the galaxy. For a crossing across tens of thousands of light years, you multiply those impacts by tens of thousands. The result is a continuous erosion process that slowly chews through whatever you built, even if you over-engineer it at the start. So your first reaction might be, fine, we'll just add more shielding, we'll put a big thick wall in front. That is actually a standard idea, a sacrificial shield. You put meters of metal or water or ice at the front of the ship and let that take the hits. The outer layers get blasted, melted, knocked away, but the crew and main structure behind stay safe for a while. This works for shorter, slower missions, and we already think about things like this for Mars trips and deep space probes. But at relativistic speeds and galactic distances, that shield has to survive millions or billions of years worth of impacts, so it has to be thick and dense and heavy. Every extra ton of shielding on the nose of your starship needs extra propulsion energy to push it. That means you need more fuel or a bigger drive, which means more structure, more mass, more complexity. The mass of the ship snowballs upward. You quickly slide into a feedback loop, where the protection you add to survive the trip makes the trip itself much harder to do. The rocket equation and the energy problem reach right back into your shielding design and choke it. Then you might say, okay, maybe we can be smart. Instead of just adding bulk, we'll use fields. A powerful magnetic field can push away charged particles, like protons and electrons, before they hit the hull. You could, in theory, create a kind of magnetic bow wave in front of the ship that sweeps out some of the plasma. That helps against ionized gas, and for slower speeds that might cut down on the radiation and particle load a lot. But dust grains are mostly neutral. They are small lumps of matter with no net charge, so they don't care about magnetic fields in the same way. They just keep coming. To deal with those, you now have to bring in extra systems like forward-facing lasers that vaporize incoming grains, or plasma shields that create a cloud of ionized gas in front of the ship to absorb hits. Every one of those systems needs power, maintenance, and active control. They are not simple passive walls. They are complicated, high-tech defenses that must operate correctly for the entire journey. And remember the timescales we're talking about. For a serious fraction of a galactic crossing, you are looking at millions of years at speed, maybe more, depending on the velocity you can reach and how many stops you make. So these shields, magnetic systems, laser brooms, and plasma buffers are not just going to run for a decade or two. They have to work for times longer than our entire species has existed. One critical failure, one long period where your shield doesn't refresh correctly, one encounter with a dense cloud that you didn't expect, and the front of your ship takes a storm of impacts that it cannot handle. So space at high speed acts like a sandblaster that never turns off. The faster you go and the longer you travel, the more severe the problem becomes. You cannot just dial up the velocity and forget about the environment. At some point, the combination of dust, gas, and enormous kinetic energy makes the ship's survival a constant fight. The scale of that fight grows with speed and distance, exactly the two things you want to increase if your goal is to cross the galaxy. And the bad news is, dust and gas are not the only things hitting you out there. There is something you cannot see, cannot dodge, and cannot entirely shield against without turning your ship into a small asteroid. A constant ocean of high-energy radiation that batters both living tissue and electronics for as long as you dare to stay between the stars. Interstellar space is not peaceful. It's a slow cooker of high-energy radiation that eats DNA and electronics over time. Start with what your body is actually built for. On Earth, natural background radiation is low. You get around 0.2 to 0.3 rem per year, which is about 2 to 3 millisieverts. Your cells can usually repair that kind of damage. Life evolved into that level of the radiation, with the atmosphere and the planet's magnetic field acting as shields. Now go up to low Earth orbit where the International Space Station flies. Astronauts there are still inside Earth's magnetic bubble, but they've lost most of the protection from the thick lower atmosphere. In 6 months, they can get something like 80 to 160 millisieverts. That's decades of ground-level exposure compressed into one mission. We already have to seriously watch their dose, limit how long they stay, and track increased lifetime cancer risk. Now leave Earth's neighbourhood entirely. When NASA's Curiosity rover was sent to Mars, the cruise through deep space let us measure the radiation environment far from Earth's shield. The readings came out to around 1.8 millisieverts per day in deep space during the trip. On the surface of Mars, under a thin atmosphere and some magnetic shielding that dropped to roughly 0.6 to 0.7 millisieverts per day. Put that together for something like a 3-year Mars round trip for humans, you get a total dose in the ballpark of 0.6 to 1 sievert. That is already near or above the current career limit many space agencies set for astronauts. At that level, the long-term risk of cancer and other radiation effects goes up a lot. A Mars mission is borderline acceptable from a radiation point of view, and that's only a few years. Now scale that out to the kind of times we've been talking about for interstellar or galactic travel. Even if you are going outrageously fast by our standards, a big trip through the galaxy takes on the order of hundreds of thousands to millions of years of travel time in the galaxy's frame. Take a daily dose in the range of half a millisievert to 2 millisieverts, which is consistent with deep space and weak shielding. Multiply that by 1,000,000 years. You're now in the tens of thousands of sieverts total dose. For humans, a few sieverts is dangerous. 10 can be lethal in a short time. Tens of thousands is so far beyond survivable that the numbers stop being meaningful for biology. DNA does not tolerate that kind of integrated beating, even if you stretch it over long times. Electronics don't do any better. High-energy particles knock bits in memory, break chemical bonds, and slowly destroy materials. Over long enough time, every chip, every sensor, every wire gets damaged again and again. Without extreme protection and constant replacement, your ship's brain and nervous system get degraded just like a living crew would. So you need shielding, serious shielding, not a thin layer of metal. To cut radiation doses by factors of 100 or 1,000, you need meters of material like water, plastic or regolith, basically space rock or soil. For a large ship, that means tens of thousands to millions of tons of shielding material wrapped around the crew and sensitive electronics. And here the earlier problems come back. Every ton of shielding adds to your mass. More mass means more propulsion energy needed to get up to speed, which means more fuel or a larger drive, which means more structure to hold it all, which means even more mass. The design spirals upward, and the energy bill from hell gets even worse. If you try to keep radiation at safe levels for millions of years, your ship starts to look less like a vehicle and more like a small artificial asteroid, extremely heavy and extremely hard to push. On top of the constant background radiation, you also have rare but violent events. Stars can produce super flares, bursts way stronger than typical solar flares, throwing intense radiation out into space. Supernovae, the explosions of massive stars, can flood nearby regions with high-energy particles and gamma rays. Gamma ray bursts, usually linked to very violent processes like merging neutron stars or certain extreme supernovae, can be lethal to biology over big distances if you are unlucky enough to be in a direct line of fire. On the scale of a few years or decades, the odds of your ship being hit by one of these extreme events might be small. Over 1,000,000 years, or 10 million, the probability that at some point you're in the wrong place at the wrong time gets much higher. It is like buying a huge number of tickets in a very bad lottery. Sooner or later, something goes off near you. If your shielding and systems are not designed to shrug off those spikes, one event can sterilize your crew, wipe your electronics, or both. So the interstellar environment is not friendly. For multi-year missions like Mars, it is already near our limits. For million-year missions, it looks fatal without absurd levels of protection. And even if you manage to shield living tissue and electronics from radiation, you still have to deal with another slow killer that never turns off: the basic wear and tear of time itself on everything you build. Because now the question becomes, even if you somehow keep people and circuits safe from particles and rays, Can any machine, any structure, any starship stay functional for millions of years in that environment without a full repair crew and a whole civilization backing it up? You're asking a machine to stay alive not for decades but for timescales longer than the existence of your species, and that changes the whole problem. Look at the best example we have right now, Voyager 1. It was launched in 1977, it's been operating for roughly 50 years, and already its instruments are failing, its memory is glitching, and we're fighting weird faults just to keep a few sensors alive. This is one of the toughest, most overbuilt, most carefully tested machines humans have ever sent into space, and half a century has already pushed it close to its limits. Now stretch that from 50 years to 5 million years, or 50 million years, and move it out into a harsher radiation environment, with no engineers, no spare parts, no ground control. The kind of starship you're talking about for a galactic crossing has to be tougher than Voyager in every way, and last for a time that makes Voyager's lifetime look like a blink. That's where basic materials physics starts working against you. Even if you build the ship out of advanced alloys and futuristic composites, the environment between the stars keeps attacking it. High-energy cosmic rays slam into the structure and knock atoms out of their positions in the crystal lattice. Dust grains, even microscopic ones, hit the hull at extreme speeds, digging tiny craters into the surface. The ship heats and cools over and over as it passes near stars or adjusts its orientation, and those thermal cycles flex every joint, every weld, every layer of material. Each of those effects, taken alone, might be manageable over years or decades. You can design around some cracking, some pitting, some slow damage, but across millions of years, every small defect grows. Micro cracks spread, embrittlement sets in, seals dry out, lubricants break down, insulation carbonizes, coatings peel. The rule becomes simple and harsh. Over long enough time, everything that can fail will fail. A structural beam that lasts 100,000 years might still fail at 200,000. A cable that survives 1,000,000 years might fail at 2,000,000. There is no such thing as a truly permanent machine. Electronics are even more fragile than the structure. Modern systems, and any advanced starship control system you'd use, rely on ultra-miniaturized components. Transistors are tiny, memory cells are tiny, and that makes them much more vulnerable to single events. A single high-energy particle can flip a bit, corrupting data, or in worse cases, cause a latch-up or burnout that permanently kills part of a chip. This already happens in satellites and probes in Earth orbit and deep space, and we defend against it using error-correcting codes, redundancy, and radiation-hardened designs. Over a few years, or even a few decades, error correction and redundancy can keep you safe. On million-year timescales, they are not enough. Redundancy just means you have multiple copies that all slowly age and get hit. Eventually, if nothing can repair or replace them, you lose them all. So the ship's electronics can't just be hardened and duplicated. They have to be part of a system that actively heals itself, that can detect damage, reroute around it, and then physically manufacture and install replacements. You're no longer talking about a computer, you're talking about an evolving, self-maintaining nervous system. At that point you realise you don't just send a ship, you send a whole ecosystem of machines. Factories, robots and AI systems that can mine raw material from asteroids or capture dust, refine it into usable metals and semiconductors, fabricate new components, disassemble failing hardware, and install fresh parts again and again without human help. Life support systems, engines, shielding, sensors, all of it has to sit inside this self-repairing industrial loop. That means your starship is basically a travelling civilization in its own right. It is not just a hunk of metal on a trajectory, it is a mobile, closed industrial economy, with supply chains, production lines, quality control and decision-making. It has to manage resources, energy and maintenance forever, or at least for as long as the mission demands. And it has to do all of that while dealing with radiation, dust impacts, possible system glitches, and slowly changing conditions in the galaxy. Even if you imagine extremely advanced AI running the show with smart diagnostics and perfect manufacturing, you're still facing the same deep problem: drift over time. Complex systems don't just sit in one perfect state. They drift. Tiny errors in fabrication, small software bugs that slip past checks, minor misalignments in sensors, they accumulate. Maybe the AI starts optimizing for the wrong thing. Maybe it slowly changes its own code in ways that are locally smart but globally dangerous. Maybe a long series of small compromises in engineering decisions leads to a design that is more fragile than the original. This is where entropy, the basic rule from thermodynamics, shows up as the final boss. Entropy says that over time, complex, ordered systems have a natural tendency to move toward disorder, unless you constantly spend energy and effort to push them back toward order. Your ship can absolutely fight entropy by repairing itself, reorganizing, rebuilding. But it has to get every critical decision right again and again for as long as the mission runs. On human timescales, you can get away with a lot. You can patch, adjust, reboot, launch a rescue mission, or retire a system before it fails. On galactic timescales, you do not get that luxury. You have to assume every backup is eventually used, every margin is eventually eaten, every component reaches the end of its life, every software stack accumulates weird edge cases. Keeping the ship in a narrow band of fully functional across millions of years under constant environmental stress starts to look less like straightforward engineering and more like a gamble you keep making over and over until the odds finally beat you. So even before you talk about people, you have a starship that has to behave like a small, stable civilization, fighting physics and statistics non-stop just to stay in one piece. And that's the optimistic version, where you assume perfect design at the beginning. Now layer actual living organisms on top of that, organisms that mutate, age, form societies and break down mentally under isolation. Because if machines struggle this much against deep time, soft, vulnerable biology trying to ride inside them has an even harder fight, and that is where the whole concept of keeping a crew alive across galaxy-scale timescales starts to fall apart completely. If your plan is just put the crew in cryosleep and wake them up at the other side, biology has some notes. Start with radiation and DNA. Even with thick shielding, some radiation always gets through. High-energy particles can slice through cells, break DNA strands, and cause small errors when the body tries to repair the damage. On Earth, that happens too, but at a low rate our biology can usually handle. Stretch that out over thousands or millions of years in deep space, and those small errors stop being rare. Across that kind of timescale, you're not just slightly raising cancer risk, you're ramping it up over and over for every generation. Then there is the environment inside the ship itself. You cannot just throw people in a metal tube with some oxygen tanks and call it done. For a long mission, you need a closed ecosystem that recycles air, water and nutrients, and grows food reliably. We tried a tiny version of that on Earth in the 1990s called Biosphere 2. It was about 3.1 acres, 1.25 hectares, sealed off from the outside with plants, soil, animals and a small human crew. Even under ideal conditions, with Earth's gravity and sunlight and immediate access to help if something went wrong, the system struggled. Oxygen levels dropped, carbon dioxide spiked, some species died off, others exploded in number, and food production became unstable. And that was over a timescale of just 2 years. Now extend that concept to a spaceship, fully closed, self-repairing with no resupply for a million-year voyage. Every leak, every pest outbreak, every failed crop, every tiny imbalance in nutrients becomes a potentially mission-ending problem. Keeping a miniature biosphere balanced for that long is far beyond anything we have done or even tested. So you might retreat to the cryosleep idea. Fine, don't run a full ecosystem, just freeze everyone and keep them on ice. Right now, we can cool certain cells, embryos, and some small animals and bring them back. But long-term suspended animation of humans is still science fiction. We do not know how to stop ice crystals from shredding tissue at large scales, how to avoid long-term chemical damage inside cells, or how to restart a complex brain after centuries or millennia without functional loss. Even if you assume a future civilization solves that biology problem, you still have to deal with the hardware that keeps those frozen passengers stable. That means refrigeration systems, power supplies, control software, monitors, backup systems, and more, all running flawlessly, not just for decades, but for geological time. Any significant failure while the crew is frozen, any unnoticed temperature rise, any slow leak, any power interruption, and your whole population quietly dies without ever waking up. Cryosleep does not remove the engineering burden, it concentrates it into a single point of failure that has to work for absurd lengths of time. So maybe don't freeze them, just keep the crew awake and have children along the way. Make it a generational ship. That sounds more organic, but it opens up a different set of problems. If the journey lasts hundreds of thousands of years, you're talking about thousands of generations. The people who arrive are not the people who left. They are the descendants of descendants of descendants. Culture is not static. Languages drift, values change. In just a few hundred years on Earth, societies can flip their priorities completely. On a ship that is isolated for tens of thousands of years, under constant resource limits, with no outside reference, culture will shift in ways you can't predict. The original mission goal, cross the galaxy and reach this specific target, becomes a legend at best. After 50,000 years, do the people on board still care about a launch decision their distant ancestors made? Or do they decide the Starship is their real home and rewrite the story around that? You could try to lock culture down with strict rules, education, and maybe even direct control of social structure, but that has its own risks. Push too hard and you get revolt, or a brittle, authoritarian system that eventually snaps. Push too little and you get drift and fragmentation. Either way, the odds that the ship's society stays aligned with the original mission for hundreds of millennia are low. The mission becomes a moving target, constantly renegotiated by people who never agreed to it in the first place. Then there is the mental side. You're asking conscious beings to live and die in a confined artificial environment, knowing they will never see a planet, never walk under an open sky, never visit the place the ship is supposedly going. For them, the destination is basically a myth, always far away, never within their personal reach. That is a very different psychological load than a 2-year mission on a space station or a 3-year Mars trip. Over long times, you have to manage boredom, depression, social conflict, inequality, resource stress, and all the subtle ways human minds react to being trapped with the same small group of people. Some will adapt, some will not. You might get sects, cults, factions that disagree on how resources should be used or what the ship's purpose really is. Any serious breakdown, mutiny, sabotage, civil war can damage critical systems or wipe out key knowledge. On a cosmic timescale, you have to assume that at least some of those breakdowns will happen. So biology fights you on every front. DNA damage builds up, ecosystems are fragile, cryosleep is unproven and dangerous, generation ships drift culturally, and the psychological cost of permanent exile is enormous. All of this stacks on top of the machine and energy problems you already had. And even if you ignore every one of those issues, even if you imagine a perfectly stable, radiation-hardened, self-healing ship with a perfectly balanced society inside, you still have to deal with one more brutal fact. Your targets are not sitting still. Stars are moving, orbits are shifting, spiral arms are rotating. The galaxy is a dynamic system, and you are trying to hit tiny moving targets on timescales where every map you make is out of date by the time you use it. You're trying to hit a target in a storm where every object is accelerating, orbiting, and being tugged by dark matter. Start with a simple correction to how most people picture space. Stars are not fixed pins on a backdrop. Our own sun is moving around the centre of the Milky Way at about 500,000 miles per hour, around 220 kilometers per second. Every other star in the galaxy also has its own motion, often tens to hundreds of kilometers per second in different directions, plus extra nudges from nearby stars, gas clouds, and the overall pull of dark matter. So when you say, let's go to that star, you're not aiming at a still dot. You're aiming at something that is racing through a constantly changing gravitational field. Over short times, like a few decades, we can track that motion pretty well. We know how nearby stars drift relative to us, and we can predict their positions for a while with good accuracy. But once you stretch the timeline into hundreds of thousands or millions of years, everything changes. Even if you started with perfect data on every star's position and velocity, those orbits slowly respond to small gravitational tugs from other stars, passing objects and the uneven distribution of mass in the galaxy. So over 1 million years, the map rots. Many of the stars you originally aimed at will no longer be where you expected. Some will have drifted far off your projected path, some will have evolved, swelling into red giants or collapsing into white dwarfs, neutron stars or black holes. Some will have exploded as supernovae. Spiral arms themselves are not rigid structures, they are density waves moving through the disk. Regions you thought would be calm might turn into active star-forming zones, and quiet stretches might get crowded. When your trip is longer than the stable prediction time for stellar motions, your navigation chart becomes a guess. To stay on target in that environment, you need to make course corrections. You can't just fire the engines once and coast in a straight line. Every time your sensors tell you that the star field is slightly off from your original plan, you have to adjust the ship's velocity and direction. That means you either brought enormous amounts of reaction mass to throw out the back for these corrections, or you rely on exotic propulsion systems that can change your vector without mass loss, and those systems have to remain fully functional for as long as the mission lasts. Each maneuver is another chance for things to go wrong. Engines can misfire, guidance systems can glitch, sensors can drift out of calibration. A series of small errors builds up over time. Over a few years, you can detect and fix that. Over 1 million years, you are stacking maneuver after maneuver, correction after correction, with no opportunity for a full reset. The probability that all of them work perfectly is not high. You might think you can get clever and let gravity do some of the work. In our own solar system, we already use gravitational assists or slingshots around planets to boost spacecraft without burning extra fuel. The same physics works with stars, black holes, and other massive objects. If you pass a star at just the right angle and speed, its gravity can bend your path and change your velocity, adding or removing energy from your trajectory. That sounds great, but here's the catch. Timing and positioning have to be incredibly precise. For a useful slingshot, the star has to be in the right place at the right time, moving in the right direction relative to your ship. On human-scale missions, we plan these windows to the day or the hour. On galactic-scale missions, those windows might be only a few thousand years wide, which sounds big until you realise your overall trip might be 1 million years or more. If your timing is off by that much, the star simply isn't in the right spot anymore. The slingshot you were counting on is gone, and you're left with the trajectory that no longer matches your original fuel and energy budget. All of this happens with no real-time navigation support from anything like GPS. On Earth, GPS works because satellites constantly broadcast signals, and you get near-instant feedback on where you are. In interstellar space, you only have starlight and maybe signals from your origin civilization, and all of that is delayed by the speed of light. By the time you see where a star appears in the sky, it has already moved. Its actual position is years to centuries ahead of the light you're seeing, depending on distance. For nearby stars, that delay is small, a few years, and you can correct for it if you know the star's motion well. But if you're trying to coordinate your path across thousands of light years, the light you see is ancient by the time it hits your sensors. You're always steering based on old information, and correcting for that requires very accurate models of how everything in the galaxy is moving. Any small error in those models grows over time, and with chaotic multi-body interactions, small errors don't stay small. So navigation becomes a high-dimensional version of the classic three-body problem, where even a simple system of 3 gravitating objects shows chaotic, hard-to-predict motion over long times. Here, you're not dealing with 3 bodies. You're dealing with hundreds of billions of stars, clouds, dark matter, and your own ship, interacting in complex ways. You can approximate the big picture, but on the level of precise long-range targeting, the chaos wins as the years pile up. That means a galaxy-crossing ship is not just fighting distance, energy, radiation, and biology. It is also fighting the fact that every target is moving under a changing gravitational landscape while your information about that landscape is permanently delayed. The farther you go and the longer you travel, the less your original map matches reality. And even if you somehow solve that, even if you build god-tier navigation systems and endlessly adjustable propulsion, there is another layer of failure waiting, one that doesn't care about your engines or your maps at all. It hits you in your ability to coordinate with the place you left and the place you are going. Because long before you finish a trip across the galaxy, your connection with the rest of your civilization stretches, then snaps, under the simple rule that nothing, not even information, outruns light. Even if you launch, your species back home falls out of your light cone long before you get anywhere interesting. Start with simple light speed delay. Proxima Centauri, the closest star to the Sun, is about 4.2 light years away. That means a radio signal moving at light speed takes about 4.2 years to get there, and another 4.2 years to come back. So if you send a "Hey, we arrived safely" message from a ship orbiting Proxima, Earth hears it more than 4 years later, and your reply to their answer comes back more than 8 years after you sent the first ping. That's for the next door star. Now stretch that across the Milky Way. The galaxy is roughly 100,000 light years across. If a ship on one side sends a message to the other side, it takes about 100,000 years for that signal to be read, and another 100,000 years for any response to make the return trip. So just one back and forth exchange is on the order of 200,000 years. Civilizations can rise, peak, and collapse completely in less time than it takes for a single "how are things" to get answered. By the time a message from your ship reaches home, the culture you're talking to might no longer exist. The language might be gone, the planet might be under different conditions, or the species that sent you might be extinct. Now, bring this down to something real you've already done. Voyager 1, your farthest probe, is only about 16.1 billion miles away from Earth right now, roughly 25.9 billion kilometers. That sounds huge, but it's still not even close to 1 light year. At that distance, the time it takes for a radio signal to get from Earth to Voyager is on the order of a day, and another day to come back. So you already see that even just outside the solar system, your control gets sluggish. A simple ping and response takes about 2 days. Now imagine that not as days, but as years, then centuries, then tens of thousands of years, as the distance climbs to interstellar and then galactic scales. That is what you're dealing with when you talk about crossing the Milky Way. There is no way around this, because nothing, including information, beats light speed in normal space. That kills the whole idea of mission control for galactic trips. For Apollo, you had Houston in constant contact, sending updated instructions, checking telemetry in almost real time. Even for Mars, you can handle delays of a few minutes to maybe an hour. On galactic scales, any update from home arrives thousands to millions of years after it's sent. If you're in trouble, by the time a warning reaches your origin world, not only is it too late, the people you're calling might be long gone. So the ship has to be fully autonomous. Its AI or its crew are not representatives waiting for orders, they are effectively their own civilization. They write their own rules, decide their own priorities, and solve their own problems with zero outside help. That's not a technical detail, that's a total change in what the mission even is. You didn't send a long expedition, you launched a splinter culture. Over time, the information itself starts to rot and drift. The science on board diverges from the science at home because they see different events, make different discoveries, and build on different data. Language shifts on the ship and on the home planet in separate ways. Cultural values split. Myths and history get rewritten differently in each place. After enough time, a message arriving from the ship to home, or home to the ship, isn't a normal communication anymore. It's closer to digging up an ancient text in a dead language. By the time any signal crosses tens of thousands of light years, the sender and receiver are separated not just by distance but by time and context. Their shared assumptions are gone, their references don't match. Even if they can decode the symbols, the meaning behind them may not land. You could easily end up with both sides seeing each other as some strange, half-understood alien culture, even though they technically came from the same original species. Now think about what that does to any dream of a galactic empire, with ships crossing the Milky Way on command. An empire is supposed to issue orders, enforce laws, coordinate big projects, keep some kind of unified structure. But if it takes 100,000 years for an order to reach one edge of your territory, and another 100,000 years to get a response, you're not running an empire, you're sending messages into archaeological time. By the time your command to adjust trajectory reaches a colony, entire systems there could have changed, multiple civilizations could have risen and fallen, and whatever ship you're trying to influence might have long since failed, arrived, mutated, or gone off on a completely different agenda. Orders arrive after events they refer to are already ancient history. Feedback loops are insanely long. You cannot run a tight, galaxy-spanning organization when communication delays are longer than the average lifespan of cultures and species. So coordinated galactic travel, fleets of ships obeying a central authority, synchronized exploration across 100,000 light-years, is already broken by basic physics, even before you talk about energy, engines, or biology. The speed of light alone guarantees that by the time you'd be able to cross the galaxy physically, you would have lost any hope of staying tightly linked with where you came from. Every long-range mission is by definition a one-way branching of civilization. And that's still not the end of the trouble, because the space you are trying to cross is not just huge, it's full of traps, gravity wells, star-forming regions, supernova zones, black holes, rogue objects, all packed into a three-dimensional maze that doesn't sit still. While your communication lines stretch and break, the terrain itself gets more dangerous the deeper you go. So the next question is simple and ugly. Even if you accept the isolation, can a ship actually thread its way through the galaxy's gravity wells and death zones without getting torn apart, cooked, or swallowed over the millions of years you would need? The galaxy isn't a flat map, it's a minefield of gravity wells, explosions, and extreme environments that you have to cross in 3 dimensions for millions of years with no reset button. Start with the bright parts, the star-forming regions. These are not calm nurseries, they are cosmic war zones. In places like giant molecular clouds and massive nebulae, you get huge, hot, young stars that pump out brutal ultraviolet radiation and powerful stellar winds. Those winds slam into gas and dust, carve out bubbles, and send shockwaves through the region. In those same regions, massive stars live fast and die young. They burn through their fuel in just a few million years and then go supernova. A single supernova can outshine an entire galaxy for a short time, and it floods nearby space with high-energy particles and radiation. If your ship passes within a few tens of light years of one of these explosions, the outer surfaces can get sterilized, coatings and materials can get fried, and systems that are not deeply shielded can take real damage. That means any path that cuts through or near active star-forming zones carries a real risk. Over a journey that lasts millions of years, the odds that at least one supernova goes off uncomfortably close to your trajectory do not stay small. You can try to plan a route that steers clear, but remember, those regions evolve, and stars that are safe when you launch can be deadly by the time you pass them. Now look toward the centre of the galaxy. The core of the Milky Way is not a friendly place. At the heart of it sits a black hole with a mass of around 4 million suns called Sagittarius A, wrapped in extremely dense clusters of stars, gas clouds, and strong magnetic fields. The stellar density there is orders of magnitude higher than in our neighbourhood. Stars whip around at high speeds, tidal forces are strong, and there's a lot of high-energy radiation and X-rays from accretion and close encounters. That region is chaotic. Orbits are tight, interactions are frequent, and the gravitational landscape changes fast. It is absolutely not the zone where you want to cruise a fragile starship and hope nothing gets flung at you. Any navigation error near the core can send you into a close pass with the black hole or throw you into a dense field of stars where collision risks and radiation spike hard. A sensible route across the galaxy would try to avoid the inner regions, but that means longer paths, more detours, and more time spent exposed elsewhere. Under all of this, the visible stars and gas aren't even most of the mass you're dealing with. The Milky Way's motion and rotation curves show that the galaxy is dominated by dark matter, an invisible component that doesn't emit light but has gravity. Dark matter forms a huge halo around the galaxy and threads through it in clumps and filaments. We can model that dark matter distribution statistically, and we can match the overall rotation speeds of stars and gas, but we don't know every local bump and lump. On a galactic crossing, your ship's path is shaped not just by the gravity of visible stars, but by this unseen halo. Small uncertainties in the mass distribution translate into small errors in the predicted gravitational pulls along your route. Over millions of years, those small errors add up. Your straight path curves more than expected, or less, and slowly drifts away from where you thought you were going. That feeds right back into your navigation and fuel problems, because you have to correct for it somehow. Then there are the hazards that don't advertise themselves with light. Rogue planets, for example, are worlds that have been kicked out of their home systems and now drift through the galaxy on their own, dark and cold. They don't shine, they barely glow in infrared, and they are extremely hard to spot at long range. Compact objects are even worse. Neutron stars and black holes without bright disks around them can be almost invisible unless you happen to catch them lensing background light or interacting with something. But they still carry a lot of mass in a small volume, and getting too close at high speed is a recipe for disaster. At 0.1 c, 10% of light speed, your ship is covering about 18,600 miles every second, 30,000 kilometers per second. Too close can mean you have just seconds or less between detecting a dark, massive object and needing to make a serious course change. Your sensors are limited by light speed too, so by the time light from that object reaches you, you're much nearer than you'd like to be. At those velocities, a tiny change in position or timing turns a safe miss into a catastrophic encounter. You might try to plan safe lanes, corridors through the galaxy where the density of stars, gas, and dangerous regions is relatively low. You choose paths that avoid the thickest star-forming clouds, stay away from the core, and don't pass near known clusters of compact objects. On paper, that makes sense. You build a galactic highway that your ships can follow. But here's the catch. Those safe lanes do not stay safe forever. Over millions of years, orbits precess, meaning they slowly rotate and shift. Star clusters move relative to each other. Spiral arms rotate around the galactic center. Gas clouds drift, collide, and break apart. New stars form, old stars die, and the distribution of mass changes. The whole disk is in motion. So by the time your ship has travelled a significant fraction of its route, the corridor you picked at launch is no longer the same. A once empty region might now be near an active star-forming complex. A quiet area could have picked up a passing cluster or a dark mass concentration. The minefield rearranges itself while you are inside it, and you're trying to adapt using information that is always delayed and incomplete. All of this means your starship is not just doing a long burn through empty space. It is threading a constantly changing maze of gravity wells, radiation zones, and invisible objects, with limited sensing range and finite time to react, at speeds where small mistakes are instantly punished. To steer around all of that, you need propulsion that can turn and brake hard when needed, not just accelerate once and coast. And that loops you right back into one of the harshest constraints hiding under everything else. Every course correction, every dodge, every emergency burn costs propellant or power. On galactic scales, you cannot just keep adding more fuel for all of those maneuvers, because the more fuel you bring, the heavier you are, and the heavier you are, the more fuel you need. You get trapped by the rocket equation, long before you ever come close to cross the galaxy territory. So the next question is brutal and simple. Even if you accept all the other risks, can you even carry, scoop, or beam in enough fuel and reaction mass to do what the trip demands? Or does the math shut you down before you leave your local neighborhood? Rocket equations are brutal. The more fuel you bring to cross the galaxy, the more fuel you need to push that fuel. Here's the core problem in plain language. For any rocket that throws stuff out the back to move forward, the speed change you can get depends on two things: how fast you can throw that exhaust out, and how heavy the ship is when it's full compared to when it's empty. That second part is the killer. To reach higher and higher speeds, the ratio of full ship to empty ship doesn't grow in a straight line, it blows up. To get to high fractions of light speed with any rocket-like system, your fuel mass has to become exponentially bigger than the actual payload you care about. Most of your Starship becomes fuel just to push more fuel. That's why chemical rockets are straight up hopeless for this job. The exhaust speed you get from burning chemical propellants is only a few kilometers per second, maybe 2 to 4 kilometers per second for typical engines, up to around 4 kilometers per second or so for the best stages, which is on the order of several thousand miles per hour. That's great for getting off Earth, great for going to orbit, great for hopping around a planetary system. But in a universe where light moves at about 186,000 miles per second, 300,000 kilometers per second, a few kilometers per second is basically standing still on interstellar scales. If you tried to design a chemically fueled ship that reaches even a tiny fraction of light speed, the rocket equation would punish you immediately. You'd need an absurd mass ratio, meaning almost everything on the vehicle is fuel, with a tiny sliver left over for structure, life support, shielding and crew. Stack more stages, it gets worse. At some point the design stops being a starship and becomes a ridiculous tower of tanks you could never actually build or launch. For galactic crossings, chemical rockets aren't just inefficient, they're a joke. So you move to the next step up in power, nuclear fusion. That's where Project Daedalus came from. The Dedalus study used an assumed exhaust speed of around 10,000 kilometers per second, roughly 6,200 miles per second, about 3% of light speed. Those numbers are insane by rocket standards, thousands of times better than chemical. Even then, Dedalus needed on the order of 50,000 tons of fusion fuel, deuterium and helium-3 to push an uncrewed probe to about 0.12 C and send it on a one-way flyby to a star just a few light years away. Look at that carefully. Tens of thousands of tons of fuel, exotic fusion hardware, and a ship the size of a small moon rocket for one robotic mission to a nearby star. No braking, no return, no people. Now scale that up. If you want to carry a crew, heavy shielding, a real habitat, and the machinery for self-repair, your dry mass explodes. To get that bulk to similar speeds, the rocket equation demands even more fuel, much more, because the mass ratio has to climb again. For a real massive arc ship, the required fuel mass starts to dwarf entire planets. Fusion helps, but not nearly enough. Then people propose ideas like Bussard ramjets, where you don't carry your fuel, you scoop it from space. The picture is simple, put a huge magnetic funnel in front of your ship, collect the thin hydrogen gas in the interstellar medium, and use fusion to burn that as you go. That sounds like it dodges the rocket equation pain, because you're not launching with all your fuel on board. But the reality check is rough. The interstellar medium is incredibly thin, usually only about 0.01 to 1 particle per cubic centimetre. That is a few atoms in a volume the size of a sugar cube. To collect enough hydrogen at high speed, you need an enormous scoop area mind-bendingly large. At those scales, the magnetic field that drags in fuel also produces drag, because you're pushing against the very material you're trying to collect. Detailed studies suggest that once you include the drag and the engineering constraints, it's very hard to make a Bussard ramjet that gives you net acceleration instead of just acting like a giant brake. The idea looks good in a quick sketch, but the numbers don't play nice. So you look at beamed power instead. Instead of carrying fuel, you put huge lasers or microwaves back home, and you push the ship with light pressure on a big sail. That's the logic behind breakthrough Starshot. If your ship is just a gram-scale chip on a thin sail, a 100 gigawatt laser array can shove it to 15 to 20% of light speed in a matter of minutes. You avoid carrying propellant, you avoid giant tanks, and the rocket equation doesn't wreck you because your engine is sitting back on your home planet. But even here, there's a hard limit. Beams spread out over the distance. Diffraction and imperfections mean that as you get farther away, the beam spot gets bigger and less intense. There's a range where you can keep pushing effectively, and then past that, the sail just coasts. That's fine for a 20-year sprint to Alpha Centauri. You accelerate for part of the way, then coast the rest. The whole trip is a few light years, and you don't care about stopping at the far end because it's a tiny probe doing a flyby. For a galaxy-crossing mission, coasting becomes a problem. If your ship spends most of a 10 million year journey in unpowered drift, you have no way to brake at the destination, no way to dodge dangers, and no way to adjust course beyond tiny nudges. To keep a big crude ship under power over tens of thousands of light years, you'd need beaming stations all along the route, on stars and platforms you haven't reached yet, built by a civilization that somehow already spans the galaxy you're trying to cross. So beamed power works beautifully as a way to send small cheap probes across nearby interstellar distances. It doesn't scale easily to megaton arc ships and 100,000 light-year journeys. Once you're out of range of your initial beam, you're on your own. And on your own in this context means drifting for time spans longer than your civilization can realistically survive. Put all of this together. Rocket-like propulsion crushes you with fuel mass. Fusion rockets improve things but still demand absurd fuel loads even for local missions. Bussard ramjets run into the reality of a thin interstellar medium and ugly drag. Beamed sails can push tiny probes to nearby stars, but they cannot babysit a huge ship across an entire galaxy unless you already have a galaxy-scale infrastructure, which is the thing you're claiming to be building. So at this point, you've run headfirst into a wall from multiple directions. The physics of propulsion, fuel and distance all say the same thing. Galaxy crossing with big ships is not just hard, it's effectively out of reach for anything like us, and even for hypothetical advanced species, the effort required begins to look insane. But there's another layer that doesn't care about your engine tech at all. Even if you handwave the propulsion limits, the energy bill, the dust, the radiation and the navigation, you still have to deal with who is running these missions, who is paying for them, and how long any civilization stays stable enough to keep trying. Because galaxies live for billions of years, and civilizations, as far as we can tell, do not. Even if physics gave you a pass, history doesn't. Species and civilizations blink in and out on timescales tiny compared to a galactic crossing. Start with your record as a species. Anatomically modern humans have been around for roughly 300,000 years. That's the full span where people with brains like yours walked the Earth. Out of that, the phase with the electricity, engines, radio, computers, rockets, and global communication is only about 200 years old. A couple of centuries of high technology versus hundreds of thousands of years of just staying alive locally. Those 200 years have already been turbulent. Now line that up against galactic time. The Milky Way is more than 10 billion years old. A mission that tries to cross a big part of it, even with optimistic speeds, takes hundreds of thousands to millions of years in the galaxy's frame. Your entire technological era so far is not even 1,000th of 1% of that. So the first problem is simple. You have no evidence that your style of civilization can stay stable for the time a galaxy-wide project needs. You actually have evidence for the opposite. Then look at the planet that supports you. Earth has been friendly enough for complex life for a few 100 million years. Multicellular organisms in the oceans, then on land, then ecosystems with forests and mammals. As the sun slowly brightens, Earth will likely stay reasonably habitable for maybe another billion years before things get so hot that oceans start to evaporate heavily and the climate tips into a runaway state that wipes out complex life. So from a habitability point of view, you might have on the order of a billion years of good enough conditions left on your home world. That sounds huge, but if a galaxy-crossing mission needs tens or hundreds of millions of years, that mission is assuming that the source civilization stays active and capable over a big fraction of that window. You're basically assuming that one culture, or an unbroken chain of related cultures, stays focused and technologically competent for something like 10% of the remaining habitable lifetime of the planet. Based on history, that's optimistic to the point of fantasy. On much shorter timescales, you already see how fragile things are. Financial crises, energy shocks, and climate events can shake global systems in just years or decades. Long-term pressures like climate change and resource depletion add more stress. You talk about collapse scenarios on timescales of decades to centuries, not millions of years. Over 1 million years, You don't get one crisis cycle, you get many. Civilizations rise, expand, hit limits and fall. New ones may appear, but they don't have to care about the projects of whoever came before them. So ask a hard question. Who keeps a galaxy-crossing project funded, staffed, and remembered through all of that? If the original civilization collapses 5,000 years after launch, does anyone in the next cycle even know the ship exists, let alone feel any duty to maintain supporting infrastructure or build follow-on missions? Over galactic timescales, you have to assume multiple rounds of rise and fall. The continuity needed to treat across the galaxy as a single, continuous plan isn't there. The same issue hits the crew. On a generational ship, where people live and die on board for thousands of generations, mission goals are not fixed. After 1,000 years, the original commanders and their children are long gone. After 10,000 years, even carefully preserved records start to feel like myths. Rituals grow around them, interpretations drift, and different factions may read the purpose very differently. From the point of view of people living on the ship, the launch is ancient history. The destination is a claim about a future none of them will personally see. The rational move is to treat the ship itself as the primary world, not the target star on some ancient chart. That only gets stronger as time goes on. After 50,000 or 100,000 years, the original mission statement is basically legend. Maybe a core group holds on to it, maybe not. The risk that the inhabitants simply abandon the original plan and redirect the ship or stop caring about navigation at all is real. On the home planet, drift happens in the other direction. After 100,000 years, the launch is deep history. After 1,000,000 years, it's prehistory, unless an unbroken chain of archivists keeps the memory alive across all collapses, wars, and cultural resets. Realistically, the starship turns into a wandering relic, cut loose from any living context. If signals from it ever arrive, the receivers might treat them as strange noise from some old era, not as live updates from an ongoing mission. This fits with the idea of a civilization half-life. Instead of asking how long one empire lasts, you ask for the typical survival time of any high-tech, space-capable culture before it changes into something else or collapses. Pick a generous number like 10,000 years or even 100,000 years as a rough median. Now compare that to travel times of millions to hundreds of millions of years. What you get is a mismatch. If the typical lifetime of a technological culture is much shorter than the time needed for a galaxy-scale project, the odds that a single coherent civilization can start, maintain, and finish that project drop towards zero. You might get many short bursts of expansion, probes sent in different directions, local colonization waves, but a single unified, we will cross the galaxy effort cannot stay intact across the full timeline. The intent falls apart long before the hardware does. So even if physics relaxed, even if engines were easier, shields lighter and navigation cleaner, you would still be stuck with the sociology and history problem. Civilizations that small and that unstable compared to a galaxy that big and that old are not good candidates for galaxy-spanning travel. And when you look at what you actually design and build today, that conclusion is reinforced hard. Every serious interstellar concept on the table now doesn't talk about crossing the whole Milky Way at all. It talks about crawling to the nearest stars with tiny probes or one-off missions and then stopping. The gap between those designs and true galactic travel isn't just a step up, it's a jump into a completely different regime. Look at every serious interstellar proposal humans have ever made. None of them even pretends to cross the galaxy. Start with the fusion giants on paper, Daedalus and Icarus. Project Daedalus from the 1970s was designed as an uncrewed fusion probe meant to reach a nearby star about 6 light-years away in roughly 50 years. It would burn around 50,000 tons of deuterium and helium-3, throw exhaust out the back at about 6,600 miles per second, 10,600 kilometers per second, and reach around 12% of light speed. That is an extreme design, orders of magnitude beyond anything we can actually build today, and it still just does a one-shot flyby of a single nearby star. Project Icarus came later as a follow-up family of concepts, also based on fusion, also targeting nearby stars at similar fractions of light speed. Different designs tweak the fuel, the staging and the mission profile, but the basic scope doesn't change. These are reach the nearest stars missions, not cross the Milky Way missions. No one writing these reports is seriously trying to map a path across 100,000 light years. The whole mindset is, can we even touch the neighbouring systems once? Then move to breakthrough Starshot, which is at the other extreme in terms of mass. Starshot goes for gram-scale payloads, little chips on ultra-thin sails, pushed by a 100 gigawatt laser array on or near Earth. The target is Alpha Centauri, about 4.4 light-years away. At around 20% of light speed, that's a 20 to 30-year trip. Fast by interstellar standards, but look at what they had to do to get there. They stripped the vehicle down to nearly nothing. These things are not starships. They do not carry people, life support, shielding, repair systems, or big instruments. They are basically high-speed robotic bullets with cameras and basic sensors. The entire concept depends on making them so light that the laser can push them to high speed without melting them or demanding absurd power levels for too long. Even then, it's one way, and it's aimed at the closest star system only. There is no serious proposal to scale this exact method straight up to megadon ships and galaxy-wide flights. So when you look at the set of human interstellar designs from Dedalus and Icarus down to Starshot, you see a clear pattern. Everything is about reaching the nearest star, or a handful of local stars with one-off missions. These are test shots, not galaxy runners. They are the equivalent of dipping a toe in the ocean, not sending fleets across it. Now think about what it would mean to scale any of these concepts up. You are not talking about multiplying by 10. To go from a few light years to something like the width of the Milky Way, you multiply distance by around 20,000. To go from a gram-scale probe to a billion-ton arc ship, you multiply mass by 1 trillion. The physics does not scale linearly over that jump. Small annoyances become hard constraints, tiny inefficiencies become fatal. What works in the nearby star regime collapses completely in the cross-the-galaxy regime. You can see the same story when you look outward. With telescopes like Hubble, the James Webb Space Telescope, and large ground-based observatories, you can watch galaxies merge, spiral arms twist, and clusters form. You see gas flowing, stars being born and dying, black holes feeding. If there were obvious galaxy-scale transportation systems, regular bright beams along fixed routes, huge artificial structures spanning large parts of a disk, huge coordinated patterns of energy use, you would expect at least a few clear, unmistakable examples. But the sky doesn't show that. You see natural structures, natural emissions, and natural chaos. There are odd objects and weird signals, sure, but nothing that screams, here is a network of starships moving across 100,000 light years under artificial control. The fact that you don't see giant, obvious transport infrastructure in any of the billions of galaxies you've looked at is a data point. It suggests that galaxy-wide travel, if it happens at all, is either extremely rare, extremely subtle, or simply not feasible in the way people casually imagine. Even your best serious science fiction and forward-looking science papers stay conservative compared to cross the galaxy. Most ambitious proposals talk about ship speeds of a few % of light speed, and travel distances of a few to maybe a few dozen light years. The language is interstellar precursor, nearby star exploration, or local neighbourhood probes. No credible technical paper says, here is how you push billions of tons of habitat, shielding and machinery across 100,000 light years with known physics. Here is the energy budget, here is the engineering path. Once in a while you see wild megastructure ideas. Dyson swarms, stellar engines, maybe moving stars themselves over long times. But even those are more about reshaping a local system or migrating a star slowly, not putting ships on scheduled runs from one edge of the galaxy to the other. So you have this mismatch. On one side, the daydream of galaxy-crossing civilizations, star empires and ships roaming from arm to arm. On the other side, the actual numbers and the actual designs, The real concepts are tiny compared to the galaxy, both in range and in mass. They stay in the local bubble because the moment you push beyond that, the energy, the time, and the engineering complexity spike to insane levels. That leads to an uncomfortable thought. If even optimistic human proposals are tiny and local, but the galaxy is billions of years old, what about species far older and more advanced than you? If crossing the galaxy were actually easy for them, if once you hit a certain level you could throw ships everywhere, wouldn't the evidence be written all over the sky by now? Wouldn't you see obvious signs of people who did not stop at the local neighbourhood? That is where all of this connects directly to the Fermi Paradox, the simple, sharp question that hangs over the night sky. If galaxy-spanning travel were really doable, where is everybody? The night sky isn't just pretty, it's suspiciously quiet. Here's the core problem in one hit. The Milky Way has hundreds of billions of stars. We now know that planets are common. Many stars have multiple worlds, some in the right temperature range for liquid water. Statistically, some of those systems should be older than ours by billions of years, with more time to evolve life, intelligence, and technology. If galaxy-spanning travel were easy, if just go faster, just build bigger actually worked, then by now the galaxy should look obviously engineered. You would expect giant structures, waste heat state signatures, weird patterns in starlight that scream, somebody has been rearranging things. You don't see that. You see a mostly natural galaxy. Now put some rough timescales on this. You don't need ships full of biological crews to spread across a galaxy. You could, in principle, use self-replicating probes. You send out robotic machines that can mine raw material, build copies of themselves, and then send those copies to new systems. If those probes cruise at just 1% of light speed, around 1,860 miles per second, 3,000 kilometers per second, that is slow compared to the speed of light, but still fast enough that they can hop from star to star in a few hundred or a few thousand years per step. Once each probe replicates, you get exponential growth in the number of machines. Under those conditions, simple models say a wave of probes could spread through the entire Milky Way in something like 10 to 100 million years. That's a long time for you, but the galaxy is over 13 billion years old. So if any civilization anywhere, at any time in the last several billion years, decided to send out self-replicators, you'd expect the wave to have had plenty of time to wash over everything, including us. But when you look around, you don't see obvious signs of that wave. There is no swarm of alien probes sitting in our solar system saying hello. The structures you see around stars match natural processes pretty well. There is no clean, sharp evidence of someone using robotic colonization fronts on galactic scale. That mismatch between this should be possible on paper and we don't see it is one version of the Fermi Paradox. Then add energy use to the picture. The Kardashev scale is a rough way to classify civilizations by how much power they harness. Type 1 uses most of the energy available on its home planet. Type 2 uses most of the power output of its star, maybe with things like Dyson swarms collecting starlight. Type 3 uses a significant fraction of the energy output of an entire galaxy. A Type 3 civilization is hard to hide. If you're tapping a galaxy's worth of stars, building large structures, rearranging orbits, or running huge power systems, you probably show up as an odd infrared signature, or you distort the normal look of a galaxy. Astronomers have looked for galaxies that are dim in visible light but bright in infrared, in a way that suggests massive engineering. And so far we don't see obvious, unambiguous examples. There are strange objects, but nothing that screams, here is a culture that turned its whole galaxy into a power plant and transport network. So you have two lines of silence, no clear colonization wave, and no clear Type 3 civilizations. That doesn't prove they don't exist, but it narrows the options. Maybe intelligent life is extremely rare. Maybe very few civilizations ever get to the point of serious spaceflight. Maybe they mostly wipe themselves out, or collapse, or lose interest before they do big things. Or, and this is the part that connects back to everything you've been hearing, maybe they do hit the same physical walls you do. The energy cost of going fast, the radiation problem, The hardware lifetime problem, the navigation chaos, the communication lag, the fuel limits, and the social fragility. All of those constraints we walked through, they are not human problems, they're physics problems. Any species built out of atoms living on a planet orbiting a star inside a galaxy has to deal with the same basic rules. If those rules make galaxy-spanning travel effectively impossible in practice, then even very advanced civilizations might be stuck in their local neighborhood, just like you. That's what makes the quiet sky so sharp. The absence of galaxy-wide empires, giant visible megastructures, and obvious colonization signatures is at least consistent with the idea that crossing the galaxy is not just unpopular but practically unreachable with normal matter and known physics. If it were easy, if it were something that naturally happens once a species hits a certain tech level, you'd expect it to have happened many times in 13 billion years. The sky does not show that. Put all the pieces together and you get a simple, harsh message. You live in a hard mode universe. The distances are huge, the speed limit is unforgiving, the energy requirements blow up as you go faster, the radiation field is hostile, entropy slowly kills your machines, biology fights you over deep time, navigation is chaotic, communication falls apart over large distances, and civilizations themselves have short, unstable lifespans compared to galactic time. All of those factors stack, none of them works in your favour. Together they carve out a region of feasible travel that is probably limited to your own system and maybe a small shell of nearby stars if you're extremely capable and extremely patient. The rest of the galaxy is still there on the sky, but functionally it might as well be behind glass. You can see it, you can study it, but you can't go there at will with big ships and living crews. So you're left with one last tempting thought, one way people try to escape all of this. What if you don't play by normal rules at all? What if there is some trick in the foundations of physics, some way to bend space itself, open shortcuts, or move information in a way that laughs at distance and light speed limits? If you had that, maybe you could jump around the galaxy. Maybe crossing it stops being about rockets and becomes something stranger. But that lands you straight in the final problem. The only real escape hatch from this entire cage is new physics we do not have, and there is no guarantee that the universe allows the kind of cheats you're hoping for. There's only one way any species crosses the galaxy in a meaningful way. Cheat. Bend space itself. And right now, that's fantasy. The big cheat codes people talk about are warp drives and wormholes. Instead of flying through space at some fraction of light speed, these ideas try to bend space-time itself. One version is the Alcubierre warp drive, where you squeeze space in front of your ship and stretch it behind. The ship itself never breaks the local light speed limit, but the bubble of space can move faster than light relative to the galaxy. Wormholes are the other big one, shortcuts that connect two distant points in space so you step in one mouth and step out the other without crossing all the distance in between. On a whiteboard, both sound like clean ways around the speed limit. But when you look at the details, the math asks for something we have never seen in nature. Matter with negative energy density, not just a lot of energy, but the opposite of normal energy. You need regions of space-time that behave like they have less than zero energy to hold a wormhole open, or to make a warp bubble stable, and the amounts involved are not small. Rough estimates say you're talking about energy on the scale of planets or stars, tied up in weird configurations, just to move one useful ship-size bubble, so you've traded one impossible demand for another. Instead of burn a star's output to push a ship to 90% of light speed, you now have assemble star-level negative energy fields and precisely shape space-time. Both are way beyond what any real engineering can reach right now. One is hard because of the rocket equation and energy. The other is hard because the required stuff may not exist in usable form at all. Then there's the deeper problem. You don't even have a complete theory for the regime where these tricks would matter. You know, general relativity, which explains gravity as curvature of space-time, and quantum mechanics, which explains particles and forces at very small scales. But you don't have a finished, experimentally checked theory of quantum gravity that merges the two cleanly. That's what you'd need to really understand if space-time shortcuts are allowed or outlawed by the universe. So right now you're in the dark. It's possible that when quantum gravity is finally nailed down, it reveals real shortcuts, stable wormholes, safe warp geometries, or something stranger. It's equally possible that every apparent shortcut is either forbidden, collapses instantly, or requires absurd conditions that no finite civilization can ever set up. The universe doesn't have to give you a hack. There is no rule that says if you get smart enough you unlock fast travel. The underlying physics can just say no. People also reach for teleportation as a way out. Not the sci-fi version where your body pops from one place to another, but the information idea. Scan a person or object in insane detail, convert that into data, send the data by radio or laser to a distant receiver, and rebuild the original from raw matter at the other end. In that picture, you don't move atoms, you move information. But that runs into brutal limits, too. A single human body has something like 10 to the 28th power atoms. To describe all of that in enough detail to reconstruct it, plus the state of your brain, you need an unimaginably huge amount of data. Scanning that without destroying it is its own nightmare. Then you have to transmit that data across space. No matter how good your compression is, the signal still can't move faster than light. You didn't beat the speed limit, you just wrapped it in engineering. On the far end, you need a machine that can take that mountain of data and assemble a matching body out of raw material with atomic precision. That machine itself is gigantic complex and needs star-level resources to run. So even teleportation as send the blueprint, not the body, doesn't give you free galaxy crossing. It gives you another energy and infrastructure problem, still capped by light speed delays. So maybe the way real advanced species cross the galaxy isn't about moving big fragile bodies at all. Maybe it's about moving information and influence. Instead of giant arc ships, they send small probes, signals, or nanomachines that can land in new systems, harvest local matter, and build new structures or new minds based on instructions sent from home. That cuts mass, and it makes each individual mission cheaper. But even that kind of virtual expansion hits the same hard walls. Your probes still can't send or receive signals faster than light. They still have to survive radiation, dust, and long timelines. A wave of small machines can spread farther than big ships, but their expansion is still capped to light speed scales, and their coordination is still broken by communication delays. This galaxy may get sprinkled with influence over billions of years, but that is not the same thing as a species cruising across it like a highway. It's slow seepage, not fast travel. When you put everything you know today on the table, the picture doesn't change much. Relativity gives you a hard speed limit. The energy needed to go near that limit becomes enormous quickly. Radiation and dust turn high-speed space into a constant assault on ships and biology. Materials and electronics don't last forever, especially under that stress. Navigation is chaotic over long times. Communication lags break control and coordination. Civilizations themselves are short-lived compared to galactic timescales. Warp drives and wormholes are interesting math toys, but they sit on top of unproven physics and require exotic conditions. Teleportation as information transfer still respects the speed of light and demands wild infrastructure. Virtual expansion hits the same light speed and hazard caps as physical expansion. Every escape route you look at either loops back to the same obstacles or leans on new physics that you do not have and might never get. So the verdict, with current physics and current understanding, is blunt. Physically crossing the Milky Way with macroscopic ships and living crews is effectively impossible. Not logically impossible in some abstract sense, but stacked so hard against you that no realistic civilization ever does it at scale. The numbers are that bad, across multiple domains. Until and unless new physics shows up, real, experimentally confirmed and actually engineerable, any species made of normal matter is probably confined to a tiny local patch of its galaxy. Maybe a home system, maybe a cluster of nearby stars, maybe a small region carved out over millions of years with probes and slow expansion, but not the whole disk, not arm to arm. The rest of the galaxy stays what it is to you right now, a distant landscape you can map with telescopes, simulate on computers, and admire in the sky, but only ever touch at the speed of light, never at the speed of travel. This video's for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.